Morning everyone, I am Tharun from Group 5 and our term paper is based on SimPB, a novel simulation based approach in the field of autonomous perception. Before diving into SimPB, I will first walk you through a few essential background concepts that are crucial for understanding the motivation and methodology behind it. These include 2D object detection. It is a fundamental computer vision task where the goal is to detect and classify objects in an image using bounding boxes on a 2D plane. It answers what objects are present and what are they in the image. Popular models include YOLO, faster RCNN, and SSD. This model process RGB images and produce 2D bounding boxes with class labels. However, they lack depth understanding, which is crucial for applications like self-driving. In contrast, 3D object detection involves identifying objects in three-dimensional space, which is important for understanding real-world spatial relationships. These models predict 3D bounding boxes that give position, size, and orientation. Inputs often include LiDAR point clouds, stereo images, or depth maps. This allows vehicles or robots to navigate safely, knowing not just where an object is in 2D, but how far and in which direction. Camera to bird's eye view transformation. This representation are essential in autonomous driving because they give a top-down spatial understanding of the environment. But cameras are perspective sensors, so bird's eye view transformation involves projecting 2D images into a top-down map. This requires estimating depth and applying geometry-based transformations. Accurate bird's eye view mapping helps in tasks like lane detection, occupancy prediction, and path planning. Now I would like to talk about DETR, a short for detection transformer, a model that fundamentally changed how we think about object detection. It is introduced by Facebook AI in 2020. DETR was the first fully end-to-end object detection model that successfully applied the transformer architecture originally designed for NLP to computer vision tasks. Traditional object detectors like faster CNN or YOLO rely on complex pipelines involving anchor boxes, non-maximum suppression, and region proposal networks. In contrast, DETR simplifies the pipeline dramatically. How does DETR work? DETR consists of two main components, a CNN backbone like ResNet to extract future maps from the input image, and a transformer encoder that takes directly the images with including a position embedding and transformer decoder that directly predicts a fixed set of objects in a single forward pass. Each object is represented by a query vector in the transformer, and the model learns to attend to different parts of image to predict bounding boxes and class labels. This allows DETR to capture global context, something convolutional detectors struggle with, making it highly effective in clustered scenes or when objects are overlapping. One of DETR's key innovation is the use of bipartite matching laws, also called Hungarian laws, which ensures a one-to-one matching between predicted objects and ground truth. This eliminates the need for post-processing steps like non-maximum suppression. Moreover, DETR performs object detection as a set prediction problem, making the output unordered and more flexible. It also naturally handles variables, numbers of objects per image. While DETR design is elegant, early versions had a drawback. Slow convergence require more epochs to train compared to traditional models. To address this, follow-up models like deformable DETR introduced deformable attention mechanisms to speed up training and improve accuracy on small objects. To sum up, DETR represents a significant shift from handcrafted detection pipelines to end-to-end attention-driven learning. It marks the beginning of the new era where vision and language model share architecture foundation, and that's exactly the kind of innovation the frameworks like SimPB are designed to build upon. All of these technologies form the foundation upon which systems like SimPB are built. In the next part of our presentation, we will explore how SimPB leverages these ideas to improve simulation and benchmarking of 3D perception models, especially in a camera-only autonomous driving systems. Thank you.
Hello everyone, myself Hardeep Gupta from Group 5. I am going to walk you through the key ideas from the paper titled SimPB, a single model for 2D and 3D object detection from multiple cameras by Yinki Tan and colleagues from Nulmex. This paper, published by researchers focused on autonomous driving, introduces a novel approach called SimPB, which stands out for its ability to simultaneously detect 2D objects in camera images and 3D objects in a bird's-eye view using a single unified model. Autonomous driving relies heavily on perception system to interpret the environment around a vehicle. Cameras are a cost-effective and critical sensor for this task. Capturing images from multiple viewpoints around the vehicle, traditionally 2D object detection identifies objects like cars or pedestrians in individual camera images, while 3D object detection maps these objects in a 3D space, often in a bird's eye view, to understand their position relative to the vehicle. The paper highlights that 2D object methods have advanced significantly multi-view 3D detection, using multiple cameras to create a comprehensive 3D understanding. Has gained traction for its ability to provide a complete picture of the surroundings. However, existing approach often use to separate 2D and 3D detectors, which introduces complexity and efficiency. For example, some methods use 2D detection results to initialize or guide 3D detection, but this is typically a one-time process, limiting the interaction between the two tasks. Let's continue our discussion forward with Abhigyan.
Moving forward, let's look at the challenges with current methods as outlined in the paper. Existing multi-view 3D detection methods can be grouped into two categories. First, the dense BEV methods, and second, sparse query-based methods. What are dense BEV methods? These transform image features from multiple cameras into a bird's eye view feature map and then apply a 3D detector. The downside? Building large BEV maps for long-range detection requires significant computational resources. Sparse query-based methods, these adapt transformer-based approaches like DETR to interact with image features directly, avoiding dense BEV maps. While efficient, these methods often rely on pre-trained 2D backbones and don't fully leverage advancements in 2D detection. Additionally, when 2D detectors are used to aid 3D detection, there are key limitations. Fragmented object representation. The 2D detectors treat the same object in different camera views as separate instances, missing the global context of the object in 3D space. Limited interaction. In two-stage methods, 2D detection results are used only once, either for selecting tokens or initializing 3D queries without iterative refinement. Optimization challenges. Combining different architectures like CNN-based 2D detectors and transformer-based 3D detectors complicates model training and optimization. Moving forward, we now introduce SimPB, a unified solution. This is where SimPB comes in, offering a groundbreaking approach to address these issues. SimPB, short for Simultaneous Perspective and BEV, is a single, unified query-based model that detects both 2D objects in the perspective view, camera images, and 3D objects in the BEV space from multiple cameras. Unlike two-stage methods, SimPB integrates 2D and 3D detection into one model, enabling continuous interaction between the two tasks. The key innovation lies in its hybrid decoder, which consists of first, the multi-view 2D decoder layers, which focus on detecting 2D objects in each camera's perspective view, and second, the 3D decoder layers, which handle 3D object detection in the BEV space. SimPB introduces two critical modules to enable seamless interaction. First, dynamic query allocation. This module maps 3D object queries to specific camera views using camera parameters, creating corresponding 2D queries for each camera. And second, adaptive query aggregation. After 2D detection, this module fuses the 2D queries back into the refined 3D queries, enabling a cyclic 3D to 2D and then forward to 3D interaction that continuously updates and improves the detection results. To further enhance performances, SimPB uses query group attention, which strengthens interactions among 2D queries within the same camera view, ensuring that queries from different cameras don't interfere with each other. Now, why SimPB matters? The paper emphasizes that SimPB's unified approach overcomes the limitations of fragmented object representation and one-time 2D to 3D interactions. By cycling between 2D and 3D detection tasks within a single model, SimPB achieves better synergy, leading to improved accuracy for both tasks. The authors tested SimPB on the new scenes dataset, a standard benchmark for autonomous driving, and report promising results for both 2D and 3D detection, which we'll explore further in later sections of the paper.
So now the what is the basic architecture of this SimPB? So we have a backbone model. As we can see, we have a backbone model. Then we have this encoder layer over here. So we have this encoder layer, then we have a hybrid decoder. So this whole thing is the hybrid decoder, and then we have temporal fusion over here. All this we'll see in detail. So the key innovation is that there is a cyclic. So first we generate 3D queries. Based on these 3D queries, we generate 2D queries, and then again with the help of these 2D queries, we update the 3D queries. So it is a cyclic approach. So it what is the evaluation? That it outstanding performance on the new scenes dataset and simultaneous improvement in both 2D and 3D detection tasks. So this is the basic overview of the architecture. So now let's see step by step this hybrid decoder module, because this is the novelty. This has many modules, and let's just explore each one of them one by one. So what is the hybrid decoder module? So it consists of a multi-view 2D decoder layers, 3D decoder input. So we have L2D layers for perspective view detection. So basically, as we can see over here, this is the hybrid decoder, and it has L decoder layers, and each of these L hybrid decoder layer consists of this 2D, this light blue box is the 2D decoder layer, and this little purplish color is the 3D decoder layer. So this is what is written, and we give it input as 3D object queries. So 3D object queries are basically just like we had object queries in the original DETR architecture, which were like kind of initial guesses. Over here also we have an input of 3D object queries, which is basically n 3D object queries, and each of them have a dimension of C. So it is an n cross C matrix, and along with the 3D object queries, we also give input as the anchor points, which consists of basically the x, y, z coordinates, the width, length, height, the orientation, x velocity, y velocity, all such things. So together this is given as an input to the hybrid decoder module. So and then how does 2D decoder work? So it is a dynamic query allocation which converts the 3D queries to 2D queries, n 3D queries to m 2D queries. We'll see all of this in detail. Then query group attention strengthens the interaction within camera groups. Then there is a 2D detection, and then adaptive query aggregation, where we reconstruct the 3D queries from 2D results, and the reconstructed 3D queries then processed. Like there's self attention, cross attention, 3D head for final 3D object attraction, and temporal cross attention for historical information. So this is the basic overview of what is there in the hybrid decoder. So now let's just see each one of this one by one. So the dynamic query allocation. So the first step, so as we can see over here, first of all, we have, this is the car, and we have multiple cameras placed on this car which are capturing different views around this car. So these are the different views. So these images are passed through a backbone model, and this backbone model is basically ResNet. So we are using ResNet, and it is generating the feature maps. So it is generating the feature maps for this each of these images, and then these feature maps are passed to the encoder layer. So they are basically flattened and they are passed through the encoder layer, and then we get some output. Okay, better representations of those feature maps from the encoder layer. So there's nothing new in this. Basically the most detailed thing is the hybrid decoder module. So now what do we do? As I told that we have these 3D object queries. So along with their anchor information, anchor queries, what do we do? there is the temporal 3D object query. So basically the past frames which have been processed, so their information is also passed, and together a cross attention is computed between the current queries which are being processed and the pre-processed frames, so that we can also keep a track of history what we saw earlier. So this is just something very basic. So we have these temporal 3D object queries. So this then together goes to this dynamic query allocation thing, which will basically convert these 3D object queries to 2D object queries. So now we are going to see this, what is dynamic query allocation. So what does it do? It allocates, so we have n 3D object, and this n is a hyperparameter. It is already predefined that n 3D object queries are there, but this M, which is the number of 2D object queries, they are dynamically learned. So we'll see how it happens. So allocate 3D object queries to different camera groups to construct 2D queries. So this is the basic purpose of dynamic query allocation, to convert these 3D object queries to one or more 2D object queries, and then group them on the basis of a camera group. So suppose we have 4 cameras. Okay, now each of these 4 cameras will capture 4 images. Okay, so that is basically V, the number of images we have, that is V. So what do? First we create an n cross m matrix. Okay, this is a mapping matrix which will help us to convert the 3D object queries to 2D object queries. So n cross m matrix, and if the I comma j entry is equal to 1, so it basically indicates that the ith 3D query is associated with the jth 2D query. Okay, and it is basically a dynamic allocation Q2D. And then what do? So we basically first create this T n cross m matrix, and then using this n cross m matrix, we just transform this 3D query vector, which consists of n cross C entries. So they basically, we can see over here, like this is n cross C matrix, this Q3D, as we saw before, that we are taking the 3D queries, each of them is having a dimension size of C, and there are n such. So this is n cross C matrix, and this T is basically n cross M matrix. So we just take a transpose of it, so it becomes M cross N. So the output is M cross C. So basically we have M 2D queries. So now what do? We take a 3D query, and then this 3D query will basically consist of 8 points, because the bounding box, because it is a 3D bounding box, though it will have 8 points. We know that a cube has 8 corner points, and there will be one center point. So because it is a 3D bounding box, so that is why it is written that we have k object points for this 3D query, that is center 8. So what do? We project, because we are dealing with 2D, so we have to project these 3-dimensional points into 2-dimensional space. So we project it onto every single image. If we have V cameras, so we'll have V images, and then we project each of these onto every single image. I hope I'm making myself clear. So now what happens? So now this projection happens with the help of camera intrinsic, like camera parameters. It's not something random. It's not like we are uniformly distributing. Suppose I have n queries, and then I have to distribute it to one or more cameras. It's not like I'm distributing some view of them to this and so on. It's basically happening through camera parameters. So basically I have a 3D query, and then I have V images, and then I project each of these queries onto each of those images. Okay, now so after projection, I'll get, if I had k object points, which is basically 9 object points, so I'll get k projections. So this is basically the projected point, and because it's the projection is on a 2-dimensional space, so therefore we have 2-dimensional points. Now how do we check whether this 3D query is related to this camera or not, or this image or not? So for that we have a validity function. So basically, if any of these points from here lie within the spatial resolution, or basically lie within this, W is the width of the image and H is the height of the image. If any of these points lie within the height and width of these image, then we consider the given 3D query valid. Basically, we consider that this 3D query is related to this camera or this image or this 2D query. Okay, so this is the validity function. So now based on this only, we try to create our n cross m matrix. So how do we create it? So we just initialize, because if I have an image, now it could be possible that all the n queries are being related to this image. So that is why initially we create an n cross n matrix, and then we dynamically allocate or remove the ones which are not related to this image. So initially we just assume that all the n queries are related to this image. That is why we create an n cross n matrix. That is why it is written vth camera. Suppose we have v camera, so I am assuming for any vth camera I create this n cross n matrix. Now based on if this query is related or not, so how am I processing it? Like, I have this n cross n matrix, and if the query which I am processing, and query is represented along the column, I am considering the column as n columns as representing the n queries. So if suppose I find out that this query, the jth query, is not related to my current image, so I'll simply put the diagonal element, I'll remove it, it will be 0. So I'll just remove it and construct t. So what is happening is, basically based on this validity function, I will check whether the jth column is valid or not in this n cross n matrix. So if my query is not related to this image, so I'll simply remove that column. Okay. So in this way, I'll construct the similar queries, m valid queries. So in this way, for my vth image, I'll get, initially my dimension was n, I had n columns. If I eliminate the redundant ones or the irrelevant ones, I'll reduce my dimension to some, suppose mv. So this is the tv matrix corresponding to the vth camera. And now what do I do? So I'll generate this t matrix for all the v cameras I have, and then I just concatenate it together. Okay, it's basically, I have suppose n cross mv for first camera, then n cross mv for second camera. So I just concatenate it side by side. I keep all those matrices side by side and just concatenate it as a big matrix, and the dimension will become n cross m. So the it's basically, m is basically the total number of 2d queries, mv is the query for vth camera, 2D number of 2D queries, and if I concatenate each one of them, I'll get the total number of 2D queries as M. Now, N is predefined, M is dynamic, as I told before. So camera parameters determine the query allocation between 2D and 3D spaces. So this was the step of how do we convert 3D queries to 2D queries. Now let's see what is the next step. So in this, after we created these 2D object queries, we pass these 2D object queries into a query group self-attention. So what does this do? So we basically group the 2D queries based on the camera. If a certain set of queries are coming or related to one camera, then they are grouped together. So this is the query group attention part. So first, what do? We have M queries. We have the total huge 2D query matrix, which has the dimension as n m cross c. Before that, after we got this T matrix, this one step is missing over here. So we just do this thing. This once this T matrix is created, so this is the step. This is what we have to do. Once this step is created, this Q, we just transform this Q 3D and generate this Q 2D. So now this 2D object queries which are generated over here, they are passed to query group attention. And what happens now? We know that Q2D has a size of m cross c. So that is why we initialize m cross m matrix, which is initially filled with zeros. And what do? Well, it is basically used to group the queries from the same camera. So what this MCG matrix will do, camera group mask attention, if I comma j, that means query I and j, they are from the same camera. So this is what this matrix will do. It will tell me that these queries are from the same camera. So attention mask. Now based on this MCG matrix, I create an attention mask because I do not want the queries which are from different camera, they interact with each other. Only the queries which are in the same camera or which are assigned to the particular camera, only they should interact. So for this purpose, I create another matrix. So what it will do, it will have 0 if the queries are from the same group, that is if I comma j is equal to 1, and it will have minus infinity. Okay. Now query group attention, self attention. So it's basically similar. I have the query matrix. I create q, k and v vectors just like we do it in normal transformer thing, and then I create this. Just before I apply softmax, what do? I just add this attention mask so that I do not pay attention to the ones which are not related to my query. So and then calculate the softmax. Rest of the steps remain the same. So where q, k, v are these m cross 2D after linear transformations. Okay, then the detection process. Now once we have created these object queries and their self attention, in the similar way we also calculate, this is group self attention. Okay, so we can see how it is being calculated. So just group after query group self attention, we also calculate the cross attention. So we have these 2D queries, we pass it through self attention module, we get some output, and then how is cross attention is basically that key and value do not come from queries. So from where do they come? So as we know that we passed this our image into backbone model, which generated some feature maps, and then this feature map went it generated the feature maps, and then what happened is that whatever feature maps, so corresponding to one camera, I'll generate some feature maps. So now the key and value come from these feature maps rather than queries. So that is what is basically cross attention. So now I get the updated 2D queries, and then what is happening, I pass them through a shared 2D head. So this 2D head is basically helping me to detect. It is basically similar to the detection transformer thing, wherein I have these 2D object queries. So they pass through a 2D object, 2D head, which basically helps me to predict the bounding box and the class. And then there is a matching between the ground truth and the predicted output. Like if suppose I have two objects in my image, so my ground truth, it will be two objects, but I can have more object queries. So the ground truth will be that. So basically the approach is similar. There's a Hungarian matching. Okay, so this was all about the query group attention thing. So once let's just see how where we are in this hybrid decoder module. So as I told you, the encoder layer generated the feature map. So now we can see the output of this feature map is going in this query group cross attention. So it is basically to compute the cross attention with the feature maps. That is why it is going over here. So we have covered, we are in this layer now. We have covered the 2D head. So as soon as it went to the 2D head, we had 2D predictions. So we can see, so the 2D predictions, so basically they are predicting the boxes in this image scene. We can see that. So the blue box, so blue, the groupings show that they are from the same camera, or red. Okay, so this is what it is happening. So we have covered till 2D detection part. Now we have the adaptive query aggregation, wherein we'll convert the 2D query back to 3D query again. So let's just see. So this is the adaptive query aggregation part. So we'll transform the 2D detection results back into 3D for subsequent 3D detection. So query extension. So what happens, just like we can see over here, just as we can see in this image, that this car is not captured completely. It is truncated. Only a part of it is seen. So the thing is that, so the queries which are truncated basically, so they'll provide very less significant information. They'll not give us the whole picture. So to overcome this, that is why we give only importance to those queries which are giving me full information. So to implement this is what we are doing over here in this adaptive query aggregation thing. So I have this 2D query matrix, and then what do? I pass it through a multi-layer perceptron feed forward network. And what does it do? It basically flags each of the query as if whether it is truncated or not truncated. Okay, so it will flag, and then I just concatenate my 2D query with these flag vectors, and then I just multiply it. So what I'll get a transformed or a manipulated Q2D matrix, and then and it will contain or it will basically the high importance will be given to those queries which are considering full information, where one sentence indicates whether 2D query is truncated or not. So now what do? We try to create the 3D query. So I have this Q2D matrix, and now this T matrix is basically remember the dimension of Q2D matrix was M cross C. So now I have to go from 2D to 3D. So the what will be the dimension of this T matrix? So it's basically N cross C. Sorry, N cross M. The dimension is N cross M. So after multiplying, my result will be N cross C. So it basically consists the information that how much weight or how much does my current 2D query relates with the or the how much does my jth 2D query relates with the ith 3D query. Okay, and so this is basically the query fusion, which is converting the 2D queries to 3D queries again. And then remember we initially also constructed a 3D query matrix, so both of them they are added together, and then we just compute a self attention on this, and this is the query 3D aggregation. So this is basically the adaptive query aggregation. Okay, so it is inverse of dynamic allocation, the truncation awareness, and we have this is as a residual connection we added. Okay, uh, so this is what is there. We have this 2D object queries. We just center indication, we pass it to MLP, and we just get the information about which one is truncated, which one is not truncated. We multiply them together and we pass it to a fusion module. We generate an output, we concatenate it with the add it with the original output, and then we pass it through a self attention on whatever aggregated. Now this aggregated 3D queries are passed through the 3D head, and they basically generate the 3D boxes in the BEV space of the image. Just we can see over here. So now we can see, so basically this was the adaptive query aggregation. So the output from here, what happened, we first computed temporal cross, which is basically, I guess it is generating the fused output. And then what is happening, it is we are calculating a temporal cross attention, then a self attention cross attention. This is basically the 3D decoder layer module it consists, and then we pass it to the 3D head, and then we calculate. So we can see that this is the bird's eye view space of multiple cameras, and then we are trying to predict the 3D objects over here, and they're constantly interacting. So this was the complete methodology of the SimPB.
Again, reviewing our PS, we were to train a unified model for both 2D and 3D object detection by optimizing a composite loss function. So let us take a look at the loss function. So the total loss is composed of L2D and L3D. L2D focuses on 2D object detection and L3D focuses on 3D object detection, including the depth supervision. So let's focus on the L2D. It is based on DETR-like approach, which treat object detection as a set prediction task. So it is composed of L DETR 2D plus lambda alpha into L alpha. So L DETR 2D is from the DETR framework, which combines Hungarian matching with classification and box regression losses. Here L alpha is the observation angle loss. It penalizes angular discrepancies between predicted and ground truth observation angles, alpha. And the formula for the same is here. And the lambda alpha, it is the balancing hyperparameter. It is set to 0.5 in experiments. Then we have N 3D loss, which is borrowed from existing 3D detection works and includes auxiliary depth map supervision, depth map supervision, and improves the localization in the BEV space. Moving on to the experiments, and the first is dataset and metrics. The dataset used was new scenes, that is 1,000 videos captured from 6 cameras with 3D ground truth annotated via LiDAR. The split was 700 training and 150 validation and 150 test. Frequency used was 2 Hz annotation. Basically, the frequency refers to the state at which annotation or labels are provided. In new scenes, each scene is labeled at 2 Hz, which means that 2 frames per second are annotated. Classes are 10 object types. 2D labels. 2D labels are back projected from 3D boxes. New scenes don't natively provide 2D bounding boxes for objects in the image space. Instead, 2D labels are derived or back projected from the annotated 3D bounding boxes using camera parameters, intrinsic and extrinsic, which was already discussed during the discussion of the working of this model. So basically, 3D bounding box is projected onto each camera's image plane, and 2D bounding box is then defined as the tightest rectangle enclosing the projected space. But it is less precise than manually annotated 2D boxes because truncation errors exist. Then the metrics, as mentioned, are used. We have for 3D detection metrics, mean average precision, new scenes detection score, mean average translation, mean average orientation error, velocity error, attribute error as such. And these metrics go beyond box matching because they evaluate the real world relevance of prediction, especially for self-driving scenarios. We also have these metrics for 2D detection, that is average precision, AP50, AP75. All these are mean precision across multiple IU threads, and these are the most commonly cited numbers. AP scores by object size, small, medium, large. They help evaluate performance across scale variations. Moving on to implementation details. So the backbone model used, uh, according to the paper, what it says is ResNet 50, ResNet 101, V299. Basically, these are the feature extractors. 50 and 101, they tell which, how many layers the ResNet is using, how many CNN layers it's using. So using 3 backbone lets authors to report small or medium or large model trade-offs. The hybrid decoder is basically a 6 layer in total, arranged as 2D to 3D in 3 cycles. They are alternating between 2D and 3D reasoning. We have already talked about it. Optimizer is ADAM-W, ADAM with decoupled weight decay. Batch size uses 48 images per iteration on 8 into NVIDIA A800 80GB. Training schedule is 100 epochs for main model, 24 epochs for quick ablations. And data handling choices, for the data handling choices, author has kept evaluation clean and reproducible. Note TTA metrics reflect a single forward pass. Gains come from architecture and not multi-scale flips. No CVGS. It is avoiding extra sampling logic, beneficial to show raw class imbalanced robustness. And no future frames, unlike video-centered methods. They demonstrate strong performance without peaking at future LiDAR timestamps. Moving on to the main results. It has been recently mentioned for 3D detection and 2D detection. So SimPB is tested on both validation and test splits for the new scenes dataset, and the results are compared with several state-of-the-art methods such as sparse 4DV3 and dynamic BEV. These all are top transformer-based performers for 3D detection and BEV maps attention mechanisms. So what were the key observations? SimPB achieves the highest performance in the all listed methods in terms of both mean average precision and new scenes detection score. The architecture is efficient. Unlike many methods, those use 6 full 3D decoder layers. SimPB only uses 3 hybrid decoder layers, each combining 1 2D layer and 1 3D layer. So the hybrid structure lets SimPB outperform other using fewer 3D specific layer, providing effectiveness for cyclic 2D and 3D interaction. Then we have perspective pre-training and improves accuracy. The model is initialized using weights pre-trained on null images, and then the performance will improve further. Here, the detailed scores are mentioned. For the 2D object detection also, we have evaluated for 2D detection performance. Even though this model is primarily designed for 3D tasks, so it has best AP scores. It achieves the highest 2D AP average precision scores among all the multi-view 3D methods that also produce 2D outputs. It is beating MV2D, it is beating Stream PETR and deformable DETR. And it is strong across all object sizes, small object or medium and large object, as mentioned in AP scores. And it is a single unified model, while other methods are separately 2D and 3D networks. But SimPB performs both tasks simultaneously using just one model. So it not only saves the computation but also ensures the consistent 2D and 3D reasoning. Now let's move on to the ablation studies. So what each experiment is teaching us, we learned here. Basically, the author systematically disable or swaps pieces of SimPV to quantify where the gains rarely come from. So we have various tables. First is hybrid decoder configuration. Basically, 6 pure 3D layers they used. Then they used 6 pure 2D layers plus 3D auxiliary loss, and then the 2D to 3D 3 cyclic ones. So what insight we got is that pure 2D or pure 3D reasoning leaves untapped queues on the table, and a cyclic 2D 3D dialog inside the decoder is what unlocks the extra 2 to 3% of MAP and NDS as mentioned in the table, the values. Then we have dynamic query allocation, like how 3D angles duplicate into per camera 2D queries. So basically, corner projections guarantee that even if the box center is outside an image, some projected points will still trigger a query, so the object gets represented in that camera. Then we have adapted query aggregation. Geometry aware diffusion plus deep supervision lets the model rebuild a sharp BEV representation instead of a blurry average of per camera views. Then we have observation angle loss weight. Small lambda alpha under penalizes orientation, and higher values overweights it. So 0.5 was a sweet spot, big orientation improvement at no MAP cost as shown by the values. So this is how lambda alpha was chosen. Then we have the generalization to other detectors. So the gains transfer even without re-engineering other parts of the pipeline, showing that SimPB's 2D to 3D coupling is a generally useful drop-in upgrade. So basically, these ablations collectively explain why SimPB surpasses previous methods, not just how much it surpasses them. Now moving on to the conclusion and limitation. So we just go to the contribution recap, that is single model data like it jointly detects 2D and 3D objects. It uses a hybrid decoder alternating and cycling processing of 2D and 3D queries. Dynamic query allocation plus adapted query aggregation is used, which enables effective transformation and refinement between 2D to 3D. And query group attention is used, which boosts intra-camera performance. But it also comes with a limitation, that is inference latency due to overhead in query allocation and aggregation due to the methods we are using. So basically, while SimPB delivers strong performance, its complex query allocation and aggregation process can introduce latency, which might hinder real-time deployment, that is, for example, in autonomous driving examples. So the paper has acknowledged this, and it proposes that the future work should aim to streamline or approximate these processes to reduce the computational overhead and make the model faster and more practical for the real world use. And it has to be more deployment friendly, basically. So this was our this was the explanation of the implementations and all the metrics they have used and the loss function they have used. That's all for group 5. Thank you.